Greetings and welcome to a new video about analog electronics, and we continue with our BJT circuits, and this is our fifth example. Next example, I would like to discuss the 4-resistor biasing, but in this case using a PNP BJT instead of the MP and BJT we have discussed in example number 4. And we will see what kind of effect the beta has also for this circuit, and also we will work out the calculations and also the simulations to verify our calculations. So let's look at our example. We have this circuit. As said, this is a PNP transistor. We have again 4 resistors, R1, R2, RC and RE. These are shown here and the values are shown here. We have one DC voltage source, which is here VEE, and we have the VEB, which is the 0.7 volt, which is here between the emitter and the base. You see it is VEB instead of VBE because that is the reverse polarity compared to the NPN transistor. So the PNP transistor has the polarities reversed compared to the NPN transistor. Because the VEC we had here before, it is now VCE. For the NPN now it is VEC. We also see that the emitter current is now flowing in this branch, and it is also the base current is flowing out, and also the collector current is flowing out. In fact, the emitter current is again the summation of the base current and the collector current. That is still valid, but it is in the reverse direction. And we also see it is in this convenient version, the emitter is in the top branch and the collector is in the bottom branch, which was also reverse for the NPN transistor. So that is briefly the discussion of the PNP compared to the NPN. Now what we want, as in the previous examples, we would like to calculate all the currents, the base current, the emitter current, and also the collector current, and also the emitter collector voltage. For the beta, which is the current gain of this transistor, 100. Then repeat the calculations for A, but then the beta is now 200, and also for beta is 300. So we have 3 cases, and we will summarize the results later. So let's look at the solutions, how to work this out. Now for this circuit we will develop at this node B the Thevenin equivalent circuit. That will be handy for the exact calculation. So this circuit will be then transformed by making the Thevenin equivalent circuit at this node. Now the Thevenin equivalent circuit has the Thevenin resistance and also the Thevenin voltage. So this part, only this part, the voltage and also the resistor, is just that Thevenin equivalent circuit. It has the resistance, which is given by the R1 in parallel R2. Why? Because when you look out of the base, which is this base node, you see the R1 in parallel with R2 when you disable all the sources. In this case it's VEE, and that will be shorted, so this is effectively ground. So you can see that B sees the R1 and R2 in parallel. That is this. Now if we now substitute the values we have given, 40 kilo ohms for the R1 and the 10 kilo ohms for R2, if you now do the math here, you will get 8 kilo ohms here for this R Thevenin. Okay, we also need this V Thevenin, the voltage, Thevenin voltage. That is just the voltage here at this node when you consider this an open circuit. So this branch is now broken. Now you see this part is actually a voltage division. So R1 over R1 plus R2 times the VEE. That's shown here. And if I now substitute the values here, you will get 16 volts. Now we have everything we require for this circuit, because this circuit will give us exact value for the base current and also the other values we can use to calculate. Now we use this circuit to develop the Kirchhoff's voltage law from the input to the output. So we will start here and make the loop, or you can also start here and make the complete loop. So if you start, for example, here, then you can say VE, this node voltage, is equal to the voltage here across the RE plus the voltage across this junction plus the voltage across RTH and also plus the voltage of the Thevenin. So that's all shown here. So the summation of 4 voltages. But we need to set up the equation, and we start with the base current. It's always handy for these kind of circuits. So I need to replace the emitter current here in terms of the base current. We know in linear regional operation, for the NPN or PNP transistor, it doesn't matter. We have this expression, beta plus 1 times the IB. Now if I now substitute this expression in this expression, collect them together, I have now this expression, which is an expression with only IB as an unknown. Why? Because I have the rest of the parameters. So if I now collect the voltages to the left side, so VE minus VEB minus the Thevenin voltage, and then collect the IB terms in one coefficient, you can see that here, and I have now an expression, and I can now set up the equation for the base current by doing the left side divided by this part of the coefficient for the IB, and then you get this expression. Okay, now we have the IB. Now we can start and begin with a beta as 100. Okay, now let's substitute the values here for VEE, VEB, and V Thevenin. This all here, you can see it's 8,000 for our Thevenin voltage, Thevenin resistance I mean. We have 1,000 for our RE, and we have now 100 plus 1, that is the beta plus 1. And the rest are also shown here. So if you now do the math, you will get 30.3 microamps. Now, since we know this is the linear region of operation, I can say also the collector current is equal to the base current times beta. In this case, it's 100, and you will get now 3.03 milliamps. Now, moving on using the emitter current expression with the beta as 100, now you will get 3.06 milliamps. So we have now three currents: base current, collector current, and also the emitter current. Next is the emitter collector voltage, EC. Now for that we set up a Kirchhoff voltage law here at the output loop. So we start again VE, but then this voltage, VRE or RE times IE using Ohm's law, and then VEC, and then also the collector resistance voltage, which is then this one. So this is Ohm's law, this is also Ohm's law, and this is the voltage drop between these two nodes. But we need this, so we can now rewrite this, and so VEC is equal to VE minus the two voltages. And if I now substitute the values here, because I know IC, I know IE, I also know the RC and RE here, given in this example also the VE is known, so this is then 10.9 volts. Now we have now everything for question A. Now we will repeat the process, exact same process for beta as 200 and then beta 300, and we will compare the results. So, moving on. We have now beta is 200. What we get? We get the exact same expression here. So we substitute, only the beta is changing. So this is not 100 anymore, but 200. So 201 in total in the parentheses, and that will give us 15.8 microamps. So it is decreasing. So we see that the base current is drastically decreasing in this case. But the IC can be again calculated using the linear region of operation formula, with this beta times the IB. And if you now do the math here also, you get 3.60 milliamps. Similarly for the IE, this formula, and it will give us the 3.70 milliamps. Okay, now we have the currents also. Again, similar thing, Kirchhoff's voltage law at the output loop. We set it up, this is the expression. We express the VEC, we substitute the values, the new values for the collector and the emitter current, and we get 10.5 volts. So you see 10.9 volts was the first case for the beta as 100, now we have 10.5. And this was 3.03 milliamps, now it is 3.60 milliamps. So you see a change, but that change is not that much compared to the change in the beta, but we will discuss this in a table also shortly. Okay, that's done. Now the final one, which is the for beta as 300. Moving on, 300. Again, the same formula for IB. We have here now the beta here, that's just the change, 300. Then we get, if you do the calculation, 10.7 microamps. For the collector current, you use the exact same formula, assuming linear region of operation. Now you will get 300 times that 10.7 microamps, you will get 3.20 milliamps. And for the emitter current, you get in a similar format 3.22 milliamps. Now again, we set up the Kirchhoff's voltage law here at the output loop, setting up the equation. We know we need VEC. Now new values for IC and IE can be substituted in this expression. You get now 10.4 volts. So we now have every unknowns here for these A, B, and C calculations. So let's give it now the summary of the results. This is the summary of the result. You can see the question ABC. 100, 200, and 300 for this beta, the current current of this PNP transistor. The base current, you can see the base current is drastically decreasing, 30.3, then 15.8, then 10.7. But what really is important is the collector current and also the emitter collector voltage, because these two values will determine the bias point, which is also called the Q point or the operating point. So you see, if I go from beta is 100 to 200, that is 100% up, this change is not that much for the collector current. It is just 13 or 0.30 milliamps. If I look at this one, that is change of 0.4 volts down. And in this case, this is just 0.04 milliamps, and here 0.1 volts. So we can say the following: the effect of variation in beta, the base current is changing drastically, but the collector current, emitter current, also the emitter collector voltage is quite stable. And that is also the reason for calling this circuit four-resistor stable biasing. But that really depends on the resistor values you have chosen. If you choose a very small value, for example, for the RC or the RE, this is not really a stable, but it is kind of a stable, but you can make it more stable when you increase the values. It also depends on the biasing point. But for this case, you see, the objective is to show you that four-resistor biasing will create a more stable situation for your IC and VEC values. Okay, DC load line equation, very important. Now, this is the equation for this DC load line. This is actually the voltage across the emitter collector nodes. This is the VEC, is equal to this expression using again Kirchhoff's voltage law here, and that is expressed in the collector and the emitter current. So the collector and the emitter current, but we like to know what is the expression or the relationship between the collector current and also the VEC. So we need to replace this. So we can say IE, emitter current, is given by the beta plus 1 times the base current. And the collector current is then given by beta times the base current. So if I now rewrite this, so base current is equal to the collector divided by the beta, and then substitute this in the expression for the emitter current, you will have this expression for emitter current in terms of the beta and IC. Now we can substitute this expression in here, so we get the following. So VEC is equal to VEE minus RC times IC, then minus RE times this expression. Instead of IE, we have an expression of IC. Now we can collect the terms and then have an expression which creates the DC load line shortly, where this is the changing variable and this is the resulting variable, which is VEC. Okay, now let's see what we get for different situation. For beta is 100, if I now substitute in here beta is 100, the RC and the RE and also the VEE, we get this expression. So VEC is 20 minus 3010 IC. Now if I now look at the beta is 200, in similar case, and it will be then 20 minus 3005 IC. Why is this a little bit changing? Because it is now beta, which is 101 over 100, and then in the second case it is 201 over 200. So it is now closer to the 1, and the summation of these two resistors RC and RE is 3000. So you get 3005, and in the first case was 3010, so a little bit an error or actual value. So in the beta is 300 case, you will now get closer to 3000, so it is now 3003. But you can say in all three cases for beta, you can say this is VEC is very close to 20 minus 3000 IC. But this is just to show you that these lines are a little bit different than the actual 3000 here. And we know that VEC is between the 0 and the VEE. These are the two extreme values for the VEC that can be taken. So it is 0 or the maximum value for this DC voltage source here. And also for the collector current, that is 0 minimum, and the maximum is the VEE divided by this total expression here in the parentheses. Okay, now we have it. Now we can use these expressions here for the VEC in terms of IC and make a plot. Now this is the IC, which is the collector current in the y-axis, and in the horizontal axis we have the VEC. Now we need a DC load line. That means we need two values, intersection to draw this line. That's for the collector is this maximum value. So if I now substitute in here the VEE, RC, RE, and also the beta, it doesn't matter which one you take. An approximate value, this is approximately 3000. Now you do 20 over 3000 or 3010 or 3005 or 3003. Now you will get this, and the other one is 20 because that is the maximum value of the VEC. Now this part is really the maximum current, which is then given by this, and that is approximately 6.65 milliamps. Okay. All right, now we have 20, which is then the maximum VEC when the current is going down to 0. Now we have now a couple of values for different betas. Now this is for the first case, when you have the beta as 100, the collector-emitter voltage, or emitter-collector voltage was 10.9, which is this row, and the corresponding IC was 3.03 milliamps, and that is now this node. So this is for beta is 100. In a similar case for beta is 200, you get this intersection with this pink line, which is our DC load line. And we have 10.5 for our VEC and 3.16 for our IC. And this is now the intersection node B. This is also called the operating point now. You see the operating point from A to B shifts a little bit to the left when the beta goes from 100 to 200, which is a large difference, 100%, but this percentage change is not that much. I will show you that later here in an extra column. Now moving on to the final one, which is the beta at 300. This new intersection here, that will give us 10.4, so a little bit to the left with the VEC, and also the current goes a little bit up, which is 3.10 milliamps. This is all shown here. And this is now the point C. So we see the operating point are really close to each other, despite the enormous change in our beta. Okay, now this is now called also the bistable. And this is now the A, B, and the C points for betas 100, 200, and 300. Now let's see also the percentage change from beta going from 100 to 200. Now in IB, the change is almost 92%, so this change. But going from the 100 to 200, in the collector current, the change is approximately 4.3%. And for the emitter current, it's just 3.8% approximately, and VEC is 3.6%. So you can say approximately the change in the collector emitter current and also the emitter collector voltage is approximately 4% change. So you change the beta from 100 to 200, which is 100% change. You only change your important parameters in your circuit by only approximately 4%. That is very stable compared to the drastically changing value of the beta. Now when you look at the situation, the change of the beta from 100 to 300, so going from this to A to C, then you see the results here. The beta IB will now have a change of 183%, very large. But that doesn't matter, we are interested in the IC and also the VEC. IC will now change from this value to that value, which is then 5.8 approximately. Emitter will be then 5.1%. And the VEC, the emitter collector voltage, will go for 4.9% change. So approximately 5.5, maybe in the extreme case 6%, when you go from 100 to 300 with a beta, which is 200% change. Again, still a very stable situation compared to the enormous change in the beta. And that's also shown here graphically in our DC load time. Okay, these are the summary of the results, and this is again a table. Now let's also look at the simulation result. This is also very important. So I will now give the circuit for each case. This is for beta as 100, and this is the circuit. You see the PNP transistor, the R1, R2, and also the RE and the RC, the values, and also the VEE, which is our DC voltage source here. I measured now the 4 values here we would like to calculate now for the beta as 100. You see the emitter current is, the base current is going here, which is 30.328 microamps, so close to what we have calculated. The collector is 3.33 milliamps, also very close to what we have in the closed vicinity. And also the IE, emitter current, is here 3.06, also very close to what we have. So those are really close values as calculated in the simulator. And the 10.87 is 10.9 approximately, which is our VEC. So we can see these are very close values. Now going to the beta as 200, the second one, which is now 15.8 for microamps for the IB. 3.16 we had calculated, is now 3.16 also approximately, and 3.18 approximately, and this is 3.17, so very close to actually also what we have, and this is 10.5, very close to 10.5 is also what we have. Now going to the next one, which is the final one, which is the beta is 300, 10.7 microamps, so also very close. 3.21 milliamps, it is 3.20 milliamps, also very close to the value we have calculated. And the 3.22 milliamps we have calculated for the emitter current, and we see also very close to that value in the simulator. You also see 10.4 approximately, or 10.37 volts, which is also what we have, approximately 10.4. So you see the simulation result do confirm the calculations very nicely, and you see 3 different values for 3 different beta of the current gain of the PNP transistor. Alright, this is for this example number 5 about the PNP transistor circuit having 4 resistors for bistable design. If you have any questions about this example or any other example in our videos in this channel, please let me know. I will try to answer them as soon as possible. In the next video we will discuss also other variations of the BJT circuit. We may also move on to the JFET and the MOSFET configurations. See you next time in another video. Take care.